Alright, Trig class, I'm home with a sick kiddo today, and I'm kind of trying to fight off a bug too, I think, so hopefully my coughing won't be too disruptive in this video. This is the final notes for section 4.1. If you do not have this note sheet, there are some on my desk at the front of my room, so go grab them. I'm not sure if you're in my room or if you're in the library or where you're at. If you don't have access to my room and cannot get the notes, make a copy from somebody else. So make sure you have these notes, either getting a copy or getting a copy from my desk. Make a copy, whatever you need to do. I'm going to start off in example 6 where we left off. Long and synthetic division was the big main ideas for this section, which we talked about in part A of this video. So if you have not watched that, go back and watch that. But I'm going to start with example 6. We started talking about the factor theorem, which really kind of branches off of the remainder theorem. So in the remainder theorem, especially like in this example up here, we can find out if this big long thing is divisible by x minus 1 by plugging in, not -1, but if I set that equal to 0, x would be equal to +1, and if I plug +1 in for x in all of the places that there's an x in this equation, and it turns out to be 0, that means that my remainder is 0. If it turns out to be 111, that means my remainder is 111. I'm not quite sure what we got as an answer. I think maybe it was the number, I don't know, 9. Was that the number 9? I'm trying to quick do some math here. I think it's the number 9. So we came to find out that it was actually equal to 9, so 9 was my remainder, which means that this guy does not go in to this one evenly. He is not a factor. That's what the factor theorem says. In order for this guy to go in there evenly, he has to have a remainder of 0, right? Like the number 2 does not go into the number 13 because it does have a remainder, but it does go into the number 14 because it has a remainder of 0, or it has no remainder. Okay, so we're looking for that remainder to be 0 in order for it to be a factor. So I'm going to start off by example 6. They say show that this thing, first and foremost, is a factor of this thing. So we know he goes in there evenly, but we have to show it. So what we're going to do is we're going to set x minus 3 equal to 0, which means that x equals 3, and we are going to plug that 3 into this equation right here. Okay, so 3 cubed minus 4 times 3 squared plus 2 times 3. And again, we're looking for this number to be 0 if it is a factor, and they're telling us that it is a factor. They're just saying show why. Okay, so our work is basically the answer to this. Okay, our answer is in the work. So 3 cubed is 27. 3 squared is 9, and 9 times 4 is -36. Then we have plus 6 plus 3. Okay, so I'm trying to do some quick math here. 27 minus 36, -9. 6 and 3 makes +9, so I have -9 plus 9, which is 0. So I have just done this part. I have just shown that this guy is a factor of that guy, because when I plug it in, he will have a remainder of 0. Okay, so that means if I were to divide this thing by x minus 3, my remainder would be 0. Okay, then the second part of this says find q of x such that x minus 3 times q of x will give me this big long thing. So in order to basically kind of get q of x by itself, I would have to divide by x minus 3, right? Divide both sides by x minus 3. So they're just basically saying, do this part, this big long thing divided by x minus 3. Okay. Now, the people that I talked with on Friday kind of came to the general consensus that they like synthetic division a lot better than long division. So anyway, we're going to do synthetic division on this thing because we can, right? X minus 3 is something that we can do using synthetic division, so we're going to go ahead and do it. So 3 is what I put on the outside, not -3, kind of like what we did over here. We set x equal to 3, so we've got to put 3 on the outside. And then my coefficients out in front, I don't have to leave any placeholders because I do have an x cubed, an x squared, an x, and a number. But my numbers out in front are 1, -4, 2, and 3. And so we're just going to do our division, and I'm going to start out by dropping down that 1 to start with. So 1 goes down here. 3 times 1 is 3. Negative 4 plus 3 is negative 1. 3 times negative 1 is negative 3. 2 and negative 3 makes negative 1. 3 and negative 1 makes negative 3. And when you add those two together, you get 0. And that's what we should have gotten. This guy should be consistent with this 0 that we get over there, okay? This part right here told us that we should get 0 as a remainder, and we did in fact get 0 as a remainder. So we're looking to see what comes out if we were to divide those. So how do we convert that back into, with all the x's and stuff in it? I looked to see, okay, we were dividing something like x to the third power by something that was x to the first power. So x to the third divided by x would leave us with x squared being the first part here, and then we just kind of go down from there. So this guy's going to be x squared, this guy is going to be x, this guy is going to be my number, and then I don't need to put anything there for a remainder, okay? So if you want to write this out nicely without the 1's in there, we really don't need the 1 in front of the x squared. So x squared minus x minus 1, that is what I get. That's what q of x, I guess, would be if we were to divide that out. That's what q of x would be. Okay, so they bump down here, and in this little box they talk about zeros, they talk about x-intercepts, they talk about solutions, okay? And then we're going to factor. A factor is just a little bit different, but zeros, x-intercepts, solutions, they all mean exactly the same thing. They're just different words for talking about exactly the same thing, okay? So we would say that since my remainder is 0, we would say that 3 is a 0 of the function of this, right? So if I would graph this guy, I know that since 3 has a remainder of 0, I know that if I were to graph him, he would have an x-intercept or a 0 or a root or a solution at that point, x equals 3, okay? So maybe my cubic function looks like this. Woo, it's kind of going through 3, whatever. But anyway, I know that he's going to touch 3 at some point, right? And maybe he touches other places too, but I know he's going to touch 3 at some point. So that's what that means, 0 x-intercept solutions. We can find those by plugging those in or doing my long division. And if it comes out as a 0 for my remainder, then he is a 0 or an x-intercept or a solution, okay? I'm going to skip example 6 or example 7 because it's really long and kind of ugly. It doesn't come out with a nice answer. So I'm going to skip that because that's going to really confuse you. You probably will have a question like that on your homework assignment. And you can try to solve it if you want to, but we can go through that one together if you have one like that on your homework assignment, and hopefully that one will be a little bit nicer. So I'm just going to save that for when I get back on, hopefully Tuesday. So, all right, next. So I'm going to come here to example 8, and it says, find 3 polynomials of different degrees that have 1, 2, 3, and negative 5 as zeros, okay? So what this means is that, well, I'm just going to worry about finding the first polynomial that has those as my zeros, okay? And then we'll talk about 3 others. So what this means is that x equals 1, x equals 2, x equals 3, and x equals negative 5. Okay, that's really what that means. And then if we go backwards, this is kind of like reverse FOIL, I guess, or reverse factoring. This is foiling, basically. Reverse factoring. If x equals 1, then that means that x minus 1 is a factor. Okay, if x equals 2, that means x minus 2 is a factor. If x equals 3, then that means x minus 3 is a factor. And if x equals negative 5, that means x plus 5 is a factor. Okay, so I know all of those things are factors. And then what we're going to do is we're going to multiply all those together. Okay, so I'm going to do this kind of in a weird order. I'm going to multiply these two, multiply those two, and then multiply these two together. Okay, so let's do that, and then it might make it go a little bit faster. So you guys should be plenty used to foiling by now. This is kind of second nature to you. X times x is x squared. I'm going to go through this kind of fast. X times negative 2, negative 2x, minus 1x plus 2. That's what he will be factored. And then if we simplify those middle two pieces, we have x squared minus 3x plus 2. Okay, some of you guys can go ahead and add those middle two steps together without having to write out that middle step, and that is a-okay too. Good for you. Okay, next one, x times x, x squared. Excuse me. x times 5 is 5x. Then we have negative 3x and negative 15. So adding those two middle pieces together, x squared plus 2x minus 15. Okay, and then after we get this, we have to multiply this guy times that guy, which is going to be a big long thing. I'm going to put it right down here underneath so I can make him written out really long. Okay, so I start with this first term and I multiply everything by the first term. So I'm going to keep going with the x squared until I'm done. So x squared times x squared is x to the fourth. X squared times 2x is plus 2x to the third. If you multiply in a different order, that is fine. You just do whatever you need to do. Okay, x squared times negative 15 is negative 15x squared. So now my x squared is done. Negative 3x times x squared is minus 3x squared, or x cubed, excuse me. I hope I didn't make a mistake. I'm kind of talking at the same time. Okay, yep, we're good. Negative 3x times 2x is negative 6x squared. And negative 3x times negative 15 is positive 45x. Okay, so that takes care of this guy. And then I have the 2, so 2x squared. And then I have 2 times 2x, so 4x. And then minus 30. Okay, last thing I'm going to combine like terms and be done. So, I'm going to write the answer up here so I don't flood down into example 9. X to the fourth, I only have one of those. So I'm going to put him up here. He is done. And then x to the thirds, I have 2 minus 3, which is negative 1. And I think that is all. So negative 1x cubed minus 1x cubed. Okay. And then x squareds, I have negative 15 minus 6, that's negative 21, plus 2, that's negative 19. So minus 19x squared. That's kind of an ugly number, but that's okay. Minus 19x squared. 45 plus 4 is 49x. And then minus 30. So this is my polynomial that has those as its given zeros. I multiply those together. Okay, now, in addition to that, it says find 3 polynomials of different degrees. So just because it has, I'm not gonna go ahead and do this process again, but just because it has these 4 as zeros doesn't necessarily mean it couldn't have another one, right? So maybe it has, maybe it has x equals 4 as a 0, in which case it would have an additional x minus 4. That would be another polynomial that would still have these guys as zeros, but it would have an additional one, okay? And I could keep adding to that. So find 3 polynomials of different degrees. So if I do that procedure where I have another one up there, then that would make this 5 degrees, right? Because I would have 5 of them to multiply together. Notice that x to the 4th power, I had 4 of them multiplied together, right? That's not a coincidence. That's just the way it goes. So if I would multiply another one, he would be x to the 5th power. And I could, keep going, and I could make him x to the 6th power if I wanted to do another x minus 1 maybe. I could keep going on forever. So that's just what that's saying by find 3 polynomials. Just because those 4 are doesn't mean he wouldn't necessarily have more than that. Okay. All right. Example 9 is just a really straight, quick answer. State the maximum number of distinct real zeros if this is my polynomial function. Okay. So when they're saying the maximum number of distinct real zeros, they're saying what's the maximum number of times he could cross the x-axis, right? Zeros are x-intercepts. So what's the maximum number of times he could cross? If he's an x to the 4th power, as his parent function, like all this other stuff is just added extra. X to the 4th power is the highest power. That means he can cross a maximum of 4 times, right? An x to the 4th power function kind of looks like a W. Okay, so that's 1, 2, 3, 4. Now, x to the 4th power might only cross 3 times, right? Maybe he goes down, but then when he goes down again, he only touches and then goes back up, right there. And there's 1, then 2, and then 3. Maybe he only crosses twice where he does this, right? And there's 1, 2. Maybe he only touches once, right? Where he does that. Or maybe he doesn't touch at all where he does this, right? So any one of those scenarios could happen. He could have 4, he could have 3, he could have 2, he could have 1, he could have 0. But it says the maximum number. So the maximum number of real zeros he can have is 4 because his highest power is 4. He could not have, let's say, 5 places where he crosses because he only has like 2 basically humps that he can do, right? So that's how that kind of works out. The highest power is the maximum number of times he can cross. And that's all. Okay.